Having seen some ideas about extrema, maximums and minimums, we're now going to try to focus on one nicely defined problem. The idea of identifying global extrema, so global max, global mins, and what's going to make our lives easier is looking at this problem when we have a closed and bounded domain. And just a reminder from the fall term, the closed means that the boundary is included, so we don't have any asymptote type behavior. We're going right up to some boundary. And bounded just means that the domain is some finite region, so we don't go out to infinity. With those two properties, we'll be able to come up with a very nice statement about where a global max or min occurs. And here it is right now. If we have a function defined on this kind of domain, so finite region with the boundaries included, then there will be global extrema, and they will occur either at one of two places. On the boundary of the domain, so on the edges, or in the interior. But if it's in the interior, we must have the gradient being the zero vector. And that is going to be something we can test for. So we can look for points where the gradient is zero in the middle, and then compare the values of the function we get there to the values of the function on the boundary, and with those two pieces of information, we'll be able to evaluate whether a function, or where the function has a global max or min. We're going to study this in the context of contour diagrams, which lend themselves very naturally to this kind of problem. For example, here's a contour diagram. Note the various heights. We have a height of 0, 20, 30, 40, 50, 60, 70, 80 towards the interior. And based on our earlier work, we found that there would be a critical point at the center of each of these points here. Sorry, a point with gradient 0. We haven't actually formalized a critical point yet, but a point of interest at the center of these various contours, these circular contours. And we know that because the value of 60, 70, 80, 90, 100 is leading up to a local maximum. If we have this nested structure of contours, we can tell in this case, because the values are going up, we're heading towards a local maximum. And likewise, 60, 70, 80, 90, 100, we're also heading towards a local maximum here. And in this set of nested values, we're actually going down into a valley because the values of the contours are going down 40, 30, 20, 10, down to 0. This would be a local minimum. And we can learn all that simply from the contour diagram. Now, the other place we were told to consider was the boundaries when we're looking for global maxima. So we know there's two hillsides here with a peak and a peak, a valley down here with a point at the lowest height possible in that valley. That would be a local min. And now we want to ask the more general question, where's the global max and the global min on this region? So if we limit ourselves only to the box shown, where's the single highest point? Global max. And where's the single lowest point? Global min. We just said on the last slide that those would occur at a point where the gradient is 0, or these points that we would have found by looking inside the nested contours, or along the boundary. So if we consider the boundary as another alternative, then we just ask ourselves, what are the heights? So compare the heights, or compare the f values, z, f, or heights at the interior local maxes and mins, and at the external boundary. Now, in this particular case, what we have for values are a local max at around z equals around 100, so above 100, z around 100. We also have another local max here that's 80, then a 90 contour, and it's around 90. And we have a local min in this valley with a value of around z equals 0. And then on the boundary, what's happening? Well, when we cross a contour on the boundary here, we would actually be at height 50. And then once we go from height 50 and we look at this contour, the next one is 60. On this whole side here, our Z is going to be between 50 and 60. And actually the same thing all the way along this side until we hit the 60 contour. In this next region, we've hit the 60 contour, so Z would be 60 there, and then it would be approaching or going closer to 70. So in this range here, we'll have Z between 60 and 70. And then it'll go back to 50 to 60, and in this range here, actually, it's going to be between 50 and 40, because those are the contours that we crossed. We're at 50 here. If I move anywhere in this region, I'm going to be heading towards height 40. Along this boundary, then we're also at height 40 too, or in the range 40 to 50. And what that means is we can compare Z values along the boundary, and those boundary Z values are between, well, the lowest they go would be 40, and the highest they go is 70. And literally, it's this simple. Is 100 bigger than 40 and 70? Absolutely. 100 is also larger than 90, so this is our global max. What's the lowest value we can get out of this entire list of points in the interior and the boundary? Z equals 0 is the lowest point. And so we can identify the global minima as being the local min we found earlier at the bottom of this valley, and the local max at 100 is the global max on the whole region. And this other max that we found is not the global max, because this point, we don't see a contour of height 100 in here. This one we do, so this point must be higher than that point. And so the single highest point, or points if they're all the same height, the single highest point is the one here, the single lowest point is in this region here. All right, let's take a look at a couple of other examples just to reinforce some of these ideas. Here's a new contour diagram, and we're going to first look for any local min and max points, and let's focus and remind ourselves here in the interior. The global max will occur at one of these local max or mins in the interior or along the boundary. And if we look here, well, remember what these points would have. These would have gradient 0. If I look carefully at this region here, I don't see any of those nested circles, and a consequence of that is any point I care to pick, I can always draw a line perpendicular to the contours and pointing uphill. So in fact, every point that I can imagine selecting in the interior here has a real directional gradient, a direction with a gradient with a magnitude and a direction. And so this particular function has no local min or max in the interior. The gradient is always defined everywhere. The gradient is always non-zero everywhere, and so there's always a point. If I pick a point, I can always go uphill in a small step, and so I can't have anything that's the lowest point or a highest point. Well, what does that leave us with? We still would be interested in what is the single highest point in this function and the single lowest point. We're going to find that by not looking at these interior points, because there are no special interior points, but we can also compare that with points in the boundary. So we're going to compare our interior points, and we don't have any local max or mins with that. But on the boundary, we can start getting some extreme values. In particular, we can see this trend up towards the corner here, and we can't say exactly where, just like with local max and min, but somewhere in the region of this corner is going to be the global max. And it's going to be with a height of Z around 260, and it's going to be on the boundary. So we said there will be a global max on a closed and bounded domain. It will be either in the interior which in this case it won't be because there are no local max or mins, or it will then be on the boundary, and this would be the single highest point. We can just follow the trend of the contours up towards that highest point. And also, we can go back down the hill and ask, oh, if I was a droplet of water dropped on here, I'd be going down, 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 and I would end up somewhere around here. And this is a global minimum, not a local. And it also occurs on the boundary. There we go. So this function has a global max and a global min. Every function on a closed and bounded region will. And they just happen to be, in this example, on the boundary rather than the interior. Last example here. Again, closed and bounded domain, and we can pretty clearly see this point here jumps out as a local to 1.51 going downhill. This would be a local minimum. It would be the only local min or max in the interior. And so if we start looking for the global max and global min, well, this pretty much has to be the global min as well. If I look anywhere else in the boundary, I get heights of 1.5 or 1, certainly values that are bigger than in the interior of this contour here. But it also means that the global max, which must exist as well, because it's a closed and bounded domain, will be somewhere on the boundary. And so if you just follow the boundary along, here we're at height 3 and then a bit higher than 3. This corner we're at height 2.5. This corner's around 1. The highest one out of all of those was at the bottom left corner. And so in this scenario, we have a mix of points on the boundary and the global min, which is in the interior. And again, we're just guaranteed that on a closed and bounded domain, we're going to have a global minimum somewhere, we're going to have a global maximum somewhere. If it is in the interior, it will be a local min, or the center of one of these sets of nested contours, or it'll appear on the boundary, in which case we'd have to actually figure out which point on the boundary is the absolute highest or absolute lowest. And that's really all there is to identifying global max and min if we have this wonderful thing of a closed and bounded domain.